How do you fix the audio?
It's only coming on my computer.
I can help with that.
I tried all the buttons there. No, there's not updated. No screen. Yeah, like just say that shoulders was external. Sorry, we'll be starting in just a minute. Technical difficulties with the audio. Will, can you say something?
Is audio on for the room?
I can do that.
Audio's on.
No, it's not. We can do that. We can also the person out. I'm kidding. You sure? I looked up this side. I can present. Yes, but oh, there we go. Yes.
Is that working?
Yeah. Can you hear us?
Fantastic. Yes, I can.
Awesome. Can you hear Tim say something?
Hello there.
Did you hear that?
That was kind of quiet. You
Okay.
might want to have the speaker just stand near the laptop.
Is
Yeah.
is a
Are
camera?
answering a question, you have to come over here because
No, the camera's just on the YouTube live stream.
And if you're asking a question, you can also just have the person next to the laptop repeat the question.
yes. Thank you, Will. Okay. Oh no. Spoilers. How do I go backwards?
Just to clarify, are you expecting questions to be interruptions or questions to be saved for the end of each section? Just to clarify.
Sounds right. Everyone
Okay.
at the end of each section. Okay, are you ready? Camera's good?
Yep. Oops.
Are we recording? Calvin, you just have to recording. What?
Are you recording that? Yeah.
Recording, transfer. Start recording. Yeah. Thanks, man. Yeah, recording will start. Okay, everyone. Hello, I'm Ryan Takui.
I'm Elizabeth Machenga.
And this is the two-stage rock competition rocket, Forte and Fortissimo.
Cool. So today we're going to go over the general overview of our project, including the mission scope, our concept of operations, and some of our top-level requirements. Then we're going to go into a little more detail of our different subsystems, including aerodynamics, structures, recovery, separation, avionics. And then we'll move on to what we're going to do testing-wise in the next few quarters and our budget estimates for this project. A general overview for our project. Our mission objective is to compete in the Friends of Amateur Rocketry competition this year with our two-stage rocket. Some of our mission success criteria include reaching an apogee as close to 2,000 feet as possible. 20,000, thank you. Record our altitude and position data. At apogee, we're going to deploy 500 milliliters of water, recover both stages of our rocket with minimal damage so they can be reflown, have a successful separation at the staging interface, and transmit live video data.
Okay, here is our open rocket of the entire model combined. We have a loaded mass of about 95. Unloaded is about 55. It is almost 14 feet long. The center of gravity and center of pressure are over there. stability is about 3.3 or 12%. And then let's look at just the sustainer. Loaded mass is only 43, unloaded 23. It's only about 7.4. This is roughly the size of the Encore rocket last year and has pretty similar specs to that. Stability is about 1.9, 10.8%. And for a little more detail, here is the full CAD model of each assembly. We have the lower stage has motor mount avionics recovery, and then the separation transition. And then same thing on the sustainer, motor mount avionics recovery, nose cone. We'll go deeper into each of those sections in a bit, but you can see the internal cross-section view of that. You can see the flight boards included and the internal skeleton on the second stage that we'll be discussing in the structure section. Here is the sustainer a bit up close. There's the skeleton that I mentioned earlier, and Tom, the flight board that we mentioned in the avionics section.
This is our concept of operations. So we have several stages that I will discuss in more detail now. So first we have our launch phase. This will include integration of Forte onto the launch rail, the start of our video and data recording, and motor ignition and liftoff. Afterwards, the booster will burn till completion, and during this we will be receiving transmitted data on the ground. After phase 3 will be our separation. This is when our separation device will be activated and our booster and sustainer will separate. After this, we will have two sequences happening at once. We'll have what happens with our booster and what happens with the sustainer. I'm going to first go over what happens to the booster. After it separates and the booster and sustainer drift apart, the booster the booster will reach its apogee and coast to about 5,360 feet. Once this happens, the avionics will detect apogee and the drogue chute will be deployed. After the booster reaches about 1,000 feet in altitude, the tender descenders will activate and deploy its main chute. And once this happens, the booster will land safely and start the GPS transmission so we can recover it after and walk through the desert aimlessly like we did last year. And then while this is happening, we will have the sustainer also continuing its flight. It will have its motor ignition and burn, which will go till completion. While this is happening, we will still be receiving that transmitted data. After the motor burns, it will be in its coast phase until it reaches its apogee. But right now we are predicting to be 20,682 feet. At this point, our water will deploy out of the nose cone as well. Once apogee is detected, the recovery will activate, the peregrine will go off and shoot out the drogue chute. And then once again, when it reaches that 1,000 feet in altitude, the main chute will deploy before it lands on the ground and starts transmitting the GPS signal.
Okay, and here I'm going to talk about the requirements. These are all our top level requirements that are derived from the competition's list of requirements, and some of these are the optional payload, or like as you'll see later, some of these are optional that get us extra points. So the competition is essentially a target apogee competition. You get more points if you are close to your apogee. It's a percentage of how close to your target you got. Our target is 20,000, and we've given it a 10% margin right now. So this is our primary objective. Next requirement is that the rocket shall be fully recoverable, because we want to get scored. If your rocket is destroyed, you do not receive points. And we'll also destroy all of our stuff that we spent so hard working on. We do not want that to happen. Going along with this is also a rocket shall be structurally stable. This is another requirement for the exact same reasons. We don't want to break our rockets. Next, we have the rocket shall maintain static stability throughout the flight. This has to do with that caliber, or stability caliber that was mentioned earlier, and we have set specific ranges for our sustainer and for our entire rocket that it's supposed to fall in, because too low is going to make it easier to push the rocket using wind or other effects. That'll cause it to not fly as high. Same way though, if the stability is too high, then it becomes more sensitive to disturbances, and it's difficult to change the trajectory once it's on a path that we don't want it to go on, then it's like game over. Next, we have the rocket shop and avionics system. This is another requirement from FAR, and it is also necessary for several of the functions of the rocket, including both our recovery systems and our separation. We need that to work as intended, and so we can get our GPS tracking telemetry. We have the rocket shall carry 500 milliliters of water. This is a fairly new FAR requirement that we did last year, so we're confident we can do it again. But it is simply the water must deploy at or after apogee from the nose cone or another part of the rocket. Next, we have the rocket's first stage and second stage shall separate from each other. This one is not necessarily a requirement from the competition, but we do get extra points like mentioned before. And we also have the second stage shall ignite after separation, and this is just a requirement to keep it, or for the two stage to not like destroy itself. Yeah, that's about it for the requirements. Now we're going to move on to all the subsystems. I'm going to let Thomas and Bryant do the aerodynamics overview if there are no questions on the full scope so far. Cool, thank you.
Yeah.
Oh, hey, Ryan.
Yeah, yes, well.
Hey, do you guys have a project timeline and where you're currently at in the project, and I guess the next steps you'll immediately take after this design review?
Yes, so each subsystem will have their own individual next steps. As for the project timeline, after PDR, we'll be preparing for CDR, which will be right when we get back from winter break or at the beginning of January, like early January, second weekend. And then as soon as we're done with CDR, we're gonna allow subsystems to start ordering all their stuff. And then by the end of January, hopefully we'll have all the materials we need. Up until May is all build season. May we'll do another check-in with all the subsystems, a little launch readiness review, see where we're at before launch at June. June is, the first weekend of June is always the launch date for the FAR competition. So that is our target. This is a 1 year long project, or we hope it's a 1 year long project. So yeah, that's our timeline. There'll be a little bit about budget in each subsystem as well as an overview at the end. And that's about everything I have. Did that answer your question?
Got it. Okay, thank you.
Yes.
Hi everyone, I'm Brian. This is Thomas. Let me start off with our motor selections. So for our stage 1 motor, which is our bottom stage, we have a Aerotech N-class motor. It has an average thrust of 1,661 newtons, a max thrust of 2,230 newtons, a burn time around 6 seconds. It's around 9 kilograms with an empty mass of around 3 kilograms, and then a length of 73 centimeters and diameter of 9.8 centimeters. For our top stage, we also have another M-class motor from Aerotech. It has a higher average thrust with it being like 1,800 newtons, a max thrust of almost 4,000 newtons, which is also higher than our bottom stage. It has a shorter burn time of 4.5 seconds. And the mass at launch would be 9 kilograms. The empty mass is around 3.5 kilograms. The length is similar, 75.1 centimeters, and it has the same diameter of 9.8 centimeters.
So moving into our flight simulations, we use three softwares in order to run our flight simulation. Firstly, with OpenRocket, and then we also did RAS Aero 2 simulations, and then we also made our own simulation within MATLAB. So firstly, we have our OpenRocket simulation. So from here, we could see that our apogee was 20,682 feet. We hit a maximum velocity of around Mach 1.4, which are around 1,500 feet per second. And then we also have our respective acceleration values, and we hit apogee at around 43 seconds. And then for this simulation, it was just basic assumptions. So we said the altitude for the launch site, which is around like 600 meters. We inputted some wind speed, and then we just used those two assumptions for temperature and atmospheric pressure. So next we have our RAS Arrow 2 simulation. So the reason we decided to use RAS Arrow in a combination with OpenRocket is because RAS Arrow has a more higher fidelity aerodynamic model. So it's going to take into account the actual fin shapes, and it's just higher fidelity overall compared to OpenRocket. And so from here we could see the apogee was slightly higher, it's 21,400 feet. Maximum velocity around 1,500, kind of matching OpenRocket there, Mach 1.4. And then also, again, a similar apogee time of around 40 seconds. And then again, we use similar assumptions to the OpenRocket model with temperature around 90 degrees Fahrenheit. And yeah. So lastly, we have our MATLAB simulation. So this plot is cropped. It doesn't have the recovery phase, just so it was easier to read. And so here we have slightly lower apogee of around 20,400 feet. It's good to note on this simulation, though, we had slightly lower expected velocity values. So you can see our max velocity was actually Mach 1.3. So that's something we're still trying to look into and figure out why that was the case. And then also we had a slightly faster time to apogee of around 37 seconds instead of 40 seconds. And for this specific model, we just use standard atmosphere, and this one actually had no disturbances with 0 wind speed.
Also, just a note on this, for this plot, we use the drag data from RAS Arrow. And we're still looking into using the drag data from OpenRocket as well to compare the two, how they compare.
Yeah. MaxQ, we're not too sure because the when we're inputting drag and that sort of stuff, we just use a exported CD versus Mach. So yeah, that's something we like Bryant was saying, because we're exporting that data, it would be nice to run our own sort of try to determine those values on our own. From CFD or something along those lines.
To add to that, MaxQ is also a structure, or mainly a structures concern, for obvious reasons. So they'll be talking a little bit about that as well.
Important for structures, it's also very important for separation.
Yes.
We use separation. I definitely have that on your charts and considering that when you're doing sports or being immersed.
Thank you.
Next, we have our wind analysis. So this is, oh, you want to?
Okay. Hello, I'm Juan. I'll be talking about wind analysis really quick. So, we've had a lot of updates to our OpenRocket in the past 24 hours. So, okay. So we have no wind, 10-mile-per-hour wind, 20-mile-per-hour wind, and 30-mile-per-hour wind as kind of our frame of references for this wind analysis, and it has also a deviation of 2 to 3 miles, so it's in that range for each. So for no wind, we see that we hit 21,340 feet, which is very much within where we want to be. Low wind, we're still in that kind of range of 20,700. And then our 20-mile-per-hour wind and 30-mile-per-hour wind, we start to see that it gets a little dicey, especially with our 30-mile-per-hour wind. So yeah, some things to take into consideration that we get from this is where, if a wind hits a certain speed, do we want to call it there?
Ours safety limits on wind speed.
Oh, I should know that off the top of my head, but I don't. I feel like it's, do you know?
15, 20 miles an hour,
Right?
somewhere in there.
Okay.
We launched at about 20 miles per
Yeah.
hour last year.
Yeah.
It was like around
very
20.
windy.
Yeah, it was pretty windy last year.
So, and those are based on past years of far as weather. So we don't expect the 30 miles per hour to launch in that conditions. We just want to consider it anyway.
Yeah. And then just a little graphic of the different iterations of the simulation. The dotted lines are goal, and then you have your series to read. Low wind is at the top, and then, or sorry, the no wind, then low wind, then 20 mile per hour, and then 30 mile per hour. And I think that's it for wind analysis.
Yeah, so our current next steps, we want to look into or have an in-depth CFD analysis to compare the drag coefficient data from OpenRocket and RAS Arrow. So we're going to be looking into that. We also want to get some drag and pressure profiles, primarily for the transition piece, which would be really nice data to have. And then also within OpenRocket and RAS Arrow, we could do angle of attack analyses. And then with our MATLAB simulation model, like I mentioned earlier, there's actually no disturbances within that model. So we'd like to potentially add those and compare them to both OpenRocket and RAS Arrow. And then we'll be moving into the airframe design, and Connor's going to come up and talk a little bit about that.
But before we move on to airframe design, are there any questions about our aerodynamics section?
Yeah, I have a few questions. Oh, is someone asking in real life?
Yeah.
Yeah.
Okay. Yeah.
Could you repeat the real life questions just so we can hear them too?
Yeah.
I was gonna about the
Yeah, separation section.
There is a separation section. It's mainly focused on the interface. As for the aerodynamic concerns, that is one of the next steps, is looking more into like the motor delay in between separation and making sure that that works with our models that we've been doing, because we kind of chose a 3-second one. We were working with the Open Rocket and designing to apogee, and then we have to go and troubleshoot and make sure that still works physically. Do you have anything else about that?
You guys looking at getting documentation on the Ajax rocket?
Yes, we did. That was one of our most referenced documents that we've been using throughout the year. And one of the things that was really interesting was that you were able to do a test motor fire to burn to see if, or before launch, like a test fire to get the actual burn time compared to what the what the spec sheet says. But we are concerned with budgets, and the motors are quite expensive now. So we are a little worried about that, not being able to get that important data.
The reason I bring that up is that the separation event on that rocket was not a safe. The second stage went unsafe after separating.
Mm-hmm.
And that would be something that I think the problem you should probably really think on trying not to have that same issue.
Yes, that is good to think about. One of the things that we did for that is the stability calipers. We made a little bit higher than what we saw on the Ajax one. That's why we have 3 for the lower and almost 2 for the upper. Compared to the Ajax one, I think it was around 2 for the overall and around 1.5 for the upper. So we upped those stabilities to try and account for that a bit, but we will definitely look more into how else to adjust that.
That's part of the reason why I asked about that. To how high your dynamic pressure is at separation is really difficult. Ideally, you would want to have very low separation so that we can stay.
Yeah, Will, what was your question?
Yeah, before I ask anything, I want to say good job with the slides. Everything looks nice and clean, especially the plot. So I can tell you guys put a lot of work. So good job to the team for that. But my first question is, I was wondering to get a little more insight into why you guys chose the M motors. Why you guys chose 2 M motors? If you had any more reasoning.
It was primarily just because of budget. If we use anything higher class, it would just be way too expensive. And then also it was just it was mainly just a budget issue, I think.
Yeah, the M1939 is the one we've used for the past 2 years on the previous rockets, and that one. So we already have the casing for that, and then also the M classes are about $500 cheaper for the grains than the N classes, and we were originally targeting 25,000, but to do that we required an N class, so we lowered our goal to 20,000 to try and do M class. Seemed more realistic with those. So that was one of our limiting requirements for the aerodynamics design, at least using M-class motors.
Got it. Okay. Did you by chance look into configuration where it's where you had like a more powerful motor for the first class and then like a less powerful motor for the second stage? Sorry, did I say class for the first stage? More powerful motor for the first stage and less for the second stage. Because just off the top of my head, thinking about this problem, it seems like you might be able to optimize like your motors better. Like if you had a more powerful motor for the bottom stage, and then a less powerful motor for the top stage, it seems like you might be able to optimize it better because you know that second stage motor, it just dead weight at the beginning of the flight. So if that was like a little less heavy, and like the first stage one was more like powerful, it seems like you might be able to optimize like cost better through that. But I was wondering if you looked into a design like that.
I think that's how it was like originally configured, but then we started running into like sourcing issues where we couldn't find like the correct configurations that would like allow us to hit our apogee point. And then just back to like the original issue, the higher power motors were just like a little bit too expensive for what we would have liked. So
Yeah, the M1939 is technically by impulse, it's an N-class motor, but it is still labeled as M for some reason. And so that is like the absolute like most powerful the M can get, or along with the other one that we chose. But we also chose the M1939 for the lower stage because of burn time. The other burn time was it was like a good 2 seconds shorter roughly. So that was another consideration. But we did consider like L configuration on top and then an M. It just was not reaching the apogee goals that we pushed. Was there a question?
Did you consider
Yeah.
clustering here?
We did consider clustering, but I did notice on the Ajax document that seemed to be one of the things that failed in the second launch. One of the J's came undone, and we were trying to avoid that. We're not experienced with that, so we're trying to do like one miracle at a time. Like the 2 stages already, that's already a big thing to go. So we don't want to try to do a cluster yet.
Yeah, adding on to that, I think one of our most main concerns while we're designing this is we don't want to have like as little single point failures as we can. And so when we have that cluster, if one motor doesn't go off or it like moves during launch, right there you have a failure, and then those just build on top of each other. So the more we can avoid having those, the better we have decided, especially because this is our team's first time building a system like this.
Sorry, was the question about clustering and launching multiple rocket engines,
Yeah.
or like in multiple motors at the same time?
Yes, sorry, we have not been doing a good job repeating the question. Yes, the question was, did we consider clustering? At least the lower stage, probably.
We're trying to type the question in the chat for the.
Thank you.
Got it. Okay. And then, you know, just going off the previous question, how much, just curious, how much would like an N motor cost? Because, you know, I remember you guys, you know, had the casing, so it's more convenient for M motor because of that. But how much did the N motor cost?
It was about 1,300 for the N motor, just for the grain. And then we'd have to buy a much larger casing that we do not have. We already have to buy one of the casings because we don't have the upper stage casing. We already have to buy one of that. And that is a huge chunk of our budget going to that. And we're trying to look into other sources of getting them a little cheaper, but it is the motors are like half the budget already. And we are trying to limit those. So using these, looking more into like N classes or higher, that's where like the budget really starts skyrocketing.
I see. Okay. And then with regards to your aerodynamic simulations and tools, so I think the big layering number that at least stood out to me was Mach 1.4. So how are you guys like accounting for that in your analysis? Because I didn't really hear anything that accounted for like the supersonic, how you guys were modeling that portion of your flight. Oh yeah, and if you guys could go back, how long was were you guys in the Mach 1 regime?
Oh, yeah, that's a good thing to add. It's not listed on these plots, but I believe we're, what was it?
It's hard to see. It's the green one.
Uh,
Couple seconds.
yeah, no, I believe it was around 7 seconds of supersonic flight, or at least the second stage, I believe. We could pull those numbers. Should be relatively easy to pull. It's just a little bit hard to see on the graph, but it was around, I think, 7 seconds around there. In terms of RAS Aero, I'm pretty sure RAS Aero has a good, they have a good supersonic flight regime for modeling. But in terms of our MATLAB simulation, we don't really have anything along those lines. It's just simply the original equations of motion from the ODE.
Yeah, that's also why I wanted to do more CFD analysis. I think that would help a lot with that supersonic region and getting like more accurate drag data around the rocket.
Okay. And then, yeah, talking more about MATLAB and this simulation you guys put. So, what are the assumptions made there, and like how did it change from last year to this year?
The main thing that changed was so previously we were only updating the density of the air from the standard atmosphere model. In this model, we're pulling density based on our Mach number instead now too, to try to like gain more of that compressibility information.
Oh yeah, also the obviously because the rocket is varying diameter, we had to incorporate that as well because the areas would change.
And then, well, are you guys modeling the stage separation also? Like, I assume it just like you decrease the mass of the second stage for the upper portion.
Yeah,
Okay.
obviously we updated the masses and all that stuff throughout the simulation. So
yeah, we have two burn ODs now.
Got it. And then wait, sorry. Your answer previously you said compressibility. Does that mean you guys modeled like the shocks? Like when you guys calculated the drag, or are you still guys taking that? Are you still taking that drag coefficient from OpenRocket and importing it into the code?
Yeah, currently we're just importing it from RAS Aero. That's why we want to do CFD for those shocks. Yeah, we didn't have time to do CFD, like a full CFD yet. We wanted to like spend a lot of time on that after this.
Okay. I think one of your next steps also, I think this might be more important than like the wind analysis for now, and then the Monte Carlo stuff too. But it's like modeling those shocks that you do encounter in like creating your own code in MATLAB. And modeling those shocks and like creating a algorithm that could like calculate the drag yourselves instead of like importing the drag profile from like RAS Aero or OpenRocket, just creating something yourselves. Because I know if I remember like looking online, I think there people did say that supersonic flight in like OpenRocket can sometimes be a little sketchy. So I think creating that own like drag algorithm that can calculate that drag to validate those other models would be a good next step you guys could take and then present during your next design review.
yeah, definitely.
Yeah, because just Mach 1.4, that was a big glaring number to me.
Either that or limit your design to less than Mach 0.8, so that you don't. To simplify it.
Is any more questions?
Hey guys, it's Jack. Can you guys hear me?
Yeah.
Cool. So I just want to say great job. It's super exciting to see the two-stage rocket in the club now. So really good analysis so far. You guys did awesome. I just had a couple like really brief little feedback points.
Mhm.
So looking at, could you go back to the RAS arrow data? Okay, cool. So that was you simulated that with 10-mile-per-hour winds. At what altitude was that? Was that sea level or at launch altitude?
2,000 feet, yeah, launch altitude.
Okay. So and I saw you guys did the wind prediction as well. Could you go to that really quick too? Okay, cool. And is this at launch altitude winds, like surface
Yes.
level winds? Okay. So the one thing that stood out to me a little bit is so with a 20,000 foot apogee, you're going to get some pretty significant upper level wind shears, in my opinion. I've never been in a club where you guys have launched over 10,000 feet. I've only worked on, you know, like Crescendo and any other rockets that go up to 10K. So my first thought is maybe you should do a little bit more research into how like upper level winds affect the flight profile. I think it'd be worth looking into, like, let's say, like taking in maybe some weather data from NOAA or from other sources and trying to develop kind of like a very rudimentary wind model in order to better predict that apogee. So that's just one thing with like high altitude rocketry you should look into a little bit more. Might be worth a little more time in future work for the project. Nothing really stood out to me in terms of technical. Does that kind of make sense to you guys?
Yeah.
Okay, cool. And then could you go to the MATLAB apogee versus the OpenRocket apogee? What were the differences there?
So MATLAB apogee was 20,392 feet, and then our Open Rocket was 20,682. So MATLAB was a
Okay,
little bit lower.
gotcha. And then okay, that looks good. That looks awesome. Kind of going off of what Will said too, the optimization for the different motors, the first thing that kind of stood out to me a little bit is I was thinking, like, my intuition was saying we should have a more powerful motor for the first stage and a less powerful for the second stage. Kind of going off of what he said, you might be able to optimize the design a little bit more that way.
Mhm.
So maybe just do a little bit more research into, you know, if we have a heavier weight motor for the first stage, you can save a lot of weight, especially on the coast phase. You'd be, you know, carrying a lot of dead weight, even though the motor's burned out. Like the bigger motors just have a you know, higher dry weight, so that could help you a little bit and optimize even like what he said, like cost as well. So that could be something worth looking into. And could you repeat, like, did you look into other alternative designs with higher power motor for the first stage?
Yeah, so like that was like our original sort of like configurations. But when we were looking into like higher power motors on the first stage, we ran into sourcing issues where like we couldn't find specific like configurations that were available. So then we kind of like moved into just using two of the same class. And then also, as Ryan mentioned, that they're cheaper. So
Also for our bottom stage, our main consideration was our burn time. And the one that we chose had the longest burn time out of all the other N-class motors that we've seen. So that was another consideration when picking those.
Gotcha. Okay, cool. Thank you. And then one last piece of feedback. Again, yeah, like what Will said, that Mach 1.4, the supersonic flight, definitely going to be, you know, a major implication for the design. Like kind of what he said, the open rocket predictions can be a bit weird with supersonic flight. So implementing kind of in your MATLAB script, maybe like super basic, like shock equations, just kind of playing around with that, trying to see if you can get that open rocket Mach to match the the MATLAB Mach reading to match the open rocket, just kind of playing around with that a little bit might be valuable. You know, you could probably implement super basic, you know, shock equations into your ODE function. So that could be worth some time as well. Have you guys have said you haven't done any kind of shock analysis yet?
no, not yet, but we can in the future.
Okay, cool. And then yeah, other than that, I wouldn't rush into CFD super quickly. You know, CFD is more of a tool for validation than prediction. So I would just, you know, focus efforts on the MATLAB, get that, you know, super nicely up, and then potentially run some CFDs toward the end. Do you guys have any questions, any of that feedback?
No, well, thank you.
Cool. Awesome. All right, nice job, guys. Great.
Thank you.
Happy to listen to it. Yeah.
I have another question. Yeah, kind of going what Jack said with the winds. I just looked back at the stability caliper for the two stages combined, and it was over 3, I guess. So I guess off the top of my head, you would think, or intuition wise, you would think that you would get a lot of wind cocking, right? Because of that high stability caliper number. Was that ever like a concern for you guys? And then you mentioned when selecting the motor just now, you guys were looking for one with a longer burn time. Did I catch that correctly?
Yeah.
Okay. Like what was the reasoning behind that? Because to avoid like wind cocking, you would normally have like a shorter burn time motor with a lot higher thrust, right? And like, was that a big factor in your design when cocking because of that stability caliper high number?
To answer the question about why we needed to choose a long burn time, there's a few reasons for that. One of the most important things is getting it off that rail and making sure once it gets off the rail, it's stable in flight. From my research, usually a longer burn time is the best for your bottom stage booster because it'll help you get that stability off the rail, get that the ideal exit velocity, and help your flight at the beginning. In terms of how high the stability is, there are a few reasons that we considered that, but I think I'll leave it to the aerodynamics team to go over that for you.
Yeah, the high stability was just a factor of we were just looking at like old or designs that have already been created, and we kind of just for example, like the Ajax rocket, we saw that their stability was lower, and we kind of just wanted to have stability that was a little bit higher. Do you have anything to add on that?
Yeah, from some like preliminary research into the design, they kind of guided our, as we kept going further, it was mainly based on the percentage rather than, or for a 2-stage rocket specifically, it was mainly based on that percent caliper rather than the like 3 point whatever cal that it is. It was mainly based on the percentage of that. So the range was we saw was about like 8 to 18 even. And ours fell within that for both of them. I think it's 10 for the sustainer and 12% for the full one. But we have not considered wind cocking yet, and that will be added into our next steps for more detailed weather and wind analysis.
And I guess that going off now, do you guys know what your velocity off the rail is going to be and like what rail size you're going to choose for these simulations?
Yes, the simulations have the 20-foot rail and the velocity off the rail. I will have to double check the number, but I believe it's 70 feet per second.
Which is the velocity we were hoping for.
At least until stage step, well, having fins in the middle of the rocket help counteract some of that wind cocking. And then once stage separation happens, you're only really worried about that upper stage. Wind cocking, or am I just maybe wrong here?
Are you asking that to us or to Will?
To Will, but both of you, I guess.
Sorry, what was the question again?
Cameron was saying, would you have to worry about wind cocking as the rocket launches? You would only really have to worry about wind cocking for the second stage because of the separation.
Well, I was just thinking because you have fins in the middle of the rocket, but I'm not an aerodynamicist, so you guys are the expert.
Well, okay, wait. Now that I'm looking at, okay, never mind. Okay, so yeah, you would have to worry about wind cocking for the 2 stages, right? Because I think your open rocket model will account for those fins in the middle and then move up the center of pressure. But even with that being said, you guys still have that stability of 3.29 for the first stage. So with that being said, I think you guys should like create your own algorithm once again to like validate what Open Rocket is telling you in terms of wind cocking. So like implement like wind in your Open Rocket. Wind in your algorithm I sent you like a little snippet of what I did, for a PSET the other day. I think you guys saw that, but yeah, I think it would be a good idea to like make your own algorithm once again, like that can gauge the severity of wind caulking. And if you guys have any like further questions, you guys can like give me a personal call about like that the code that I sent. But yeah, I think it'd be good to like develop something on your own once again and validate the result you guys are seeing from these softwares.
Yeah, for sure. Yeah. Any more questions?
I was just wondering one more thing real quick.
Yeah.
Just out of curiosity, for this stage separation, did you all model like a certain delay for that?
Yeah, the
Or how
MATLAB,
does that work?
the OpenRock, all the simulations are modeled after a 3-second delay.
Okay, and that's what you plan to use?
Yeah, and separation occurs at burnout.
Gotcha. Cool.
Okay, so now we're just gonna move into the airframe design. Yeah. So I'm Connor. I'm gonna be going over the airframe design, and this is the overall model that of the rocket that you saw in one of the previous slides. For the nose cone, we're going to be using a Von Karman hack series with a length of 13 inches and inner diameter of 5 inches, a wall thickness of about 0.08 inches, and a neck length of 2 inches. And something to note is that on the figures, there's an internal neck shown, but it's actually going to be an external neck. And then it's going to be the same water release system as last year's rocket Encore, where once it reaches apogee, the rocket is gonna rotate and it's gonna the tip's gonna separate from the transition and release the 500 milliliters of water. And then for manufacturing, the nose cone is going to be made with 6061 aluminum on a lathe, and the transition is going to be made with the carbon fiber layup.
Have you discussed in our structure section?
The question was, how hot is the nose cone tip going to get? And that there is analysis for that in the structures section. Yeah, so stay tuned.
And then for the body tubes for the sustainer, all of them are going to have an inner diameter of 5 inches and a wall thickness of 0.08 inches. The recovery tube is going to have a length of 22 inches. Avionics is going to have a length of 18 inches, and the motor tube is going to have a length of 34 inches. And all are going to be manufactured with carbon fiber pre-peg on their respective tubes.
Sorry, there's a correction there. The avionics one is not.
Oh, fiberglass.
Fiberglass wet layup.
Avionics to be made with fiberglass.
And the reason it's on a foam roller is because it got stuck on the mandrel last time we tried that, but it came off the foam roller really easily. So we're doing that again.
And then for the sustainer fins, the ripcord is going to be about 9.8 inches. The tip cord is going to be around 2.8 inches. The height's going to be 4.3 inches, and the thickness is going to be about 0.2 inches. And this is going to have a foot and putter of about 1.5. And it's going to be manufactured by cutting pre-peg on a water jet. For the stage transition, the length is going to be 6.6 inches. The 4 inner diameter connecting the sustainer is going to be 5 inches. The aft inner diameter connecting the booster stage is going to be 6 inches with a wall thickness of 0.12. And then the neck lengths are going to be 2 inches on the recovery side and 1.6 inches on the separation side. And this is also going to be made with carbon fiber wet layups. And then for the That should be 6. Yeah. For the booster, body tubes, all of the inner diameter is gonna be 6 inches. The wall thickness is gonna be 0.12 inches, and the recovery and avionics tube are gonna have a length of 18 inches, and the motor tube's gonna have a length of 32.5 inches. And then they're gonna be manufactured the same way as the sustainer body tubes, where the recovery and motor tubes are gonna be made with carbon fiber prepeg, and the avionics is gonna be made with fiberglass wet layups. And then for the booster fins, the root core is going to be 12.6 inches. The tip core is going to be 4 inches. The height's going to be 6 inches, and the thickness is going to be 0.2 inches with a flint footer of Mach 0.86. And they're also going to be made the same way as the sustainer fins with cutting prepeg layups on a water jet. And here's our bill of materials. You can see the 2 motors and the casing are relatively expensive. We're still looking, these prices are sourced directly from Aerotech. So we're still looking into getting potentially cheaper options, but this is what we're looking at right now. And yeah, our total is around $2,800, $2,900. And yeah.
So I guess my question, so both of your motors are 9.8 or 98 millimeters.
Yes.
Then why do you need to neck down? Like
Just to decrease drag for the upper stage. Because if it was, we did simulate it with 6-inch diameter, like constant, and it did not hit the correct altitude.
5-inch constant. It was concerned with like spacing on the lower stage. We were running out of like room for all the avionics and or like the separation stuff with the recovery stuff. We were having issues trying to get that working. Does having a larger diameter per stage mean that on the rail, the second stage isn't supported at all? Other than
Yes.
Calvin says yes. He is our structures lead, so we trust him. That is a very good point. Is there a recommendation off the top of my head? Moving the rail buttons might help with that a little bit. No, there's a couple ways to do it. That you could get it to work, but there's trades that all have their positive and negative. Probably not the right time to have the conversation. Okay.
Is there any final thoughts or questions for aerodynamics?
I guess one of the other things for the trade between like 5-inch versus 6-inch booster stage, like was the like packing efficiency, like why did you choose to go wider, like a wider diameter over the entire length versus say making a longer first stage and having a larger interstage area?
I think part of that was due to the fact that we're 14 feet long, and we were having worries about bending of the entire rocket.
Yeah, I mean, did you guys do like stiffness analysis, but are you gonna go over the stiffness of the entire assembly?
That is the structure's future goal, I think, yeah.
We discussed bending in the structure section, but there's still a few more analysis of like the overall like properties of our body tube and system.
Sorry, real
yeah.
quick. I had a question on the booster fin flutter Mach number.
Mhm.
I think looking at your graphs from the simulations, you might be exceeding that number at separation or leading up to separation.
So basically that fin flutter is based on, or the, when I looked, it was 0.7.
Okay.
Or Mach 0.7 was the max that the first stage would reach because, or yeah, that's before when they separate, that's when it accelerates and gets like Mach 1
0.5.
Okay, yeah,
when it
I was
that.
just trying to read it off a graph and
Yeah, sorry, it was a little unclear in the picture.
no,
Ba-
that was
but
just a
based on
concern
what
I
I
had,
saw,
wanted to check.
yeah, thank you. Based on it, it was like 0.7. The safety margin's about 15%. So the real mock, like the fin flutter becomes a concern at like 1. So our safety margin of 0.86, and then with even lower or with our fins only reaching like 0.7, we felt comfortable with that.
Yeah, that sounds good. Thank you for pointing out what the number is from the graph.
Yes.
Again, I was just doing my best to read it, and having you guys confirm what it is helps a lot.
Okay, now we're gonna be moving into structures, so, Kendall and, or, Kendall, just Calvin.
Kendall's online.
Oh, okay.
Yeah. Calvin's coming up. Thanks, aerodynamics.
Yeah. Hi guys, I'm Calvin. Kendall is my co-lead and she is online right now. She couldn't make it in person, but we will be going through some structure stuff. Just click. Okay. So first off, like general materials overview, we're using 6061 aluminum. That's what we've been using in the past. It's reliable and easily manufacturable, which is what we care the most about because we will be making our parts by scratch. Also, there may be some 70/50 aluminum stock that we have in the shops. That would be very helpful for us, and we will talk about that more later because aluminum is expensive. We will also be using fiberglass for our avionics body tubes because that's what's required for signals to get through. And at this point, our fiberglass is significantly less strong than carbon fiber. So for the second stage, we will have to rely on the internal skeleton to support that load in that section, and we will get into that as well. With our carbon fiber, there's a lot of pros, not a lot of cons for carbon fiber. And now that we've been able to water jet the past couple years, it makes it a lot easier for us to make pretty precise shapes out of carbon fiber as well, as opposed to sloppy layups that might happen. So yeah. And rail buttons, that was briefly mentioned as an issue. Our CG is right at the top of the first stage. And the rail buttons are supposed to straddle the CG to support that. So we are going to have to figure out a way to mount our top rail button either at the CG or right above the CG at that separation state, or finding other ways to mount it on the second stage. We're going to use 1515 rail buttons. They're planned for a 20-inch launch rail that they have at FAR. FAR also has a 20-foot launch rail at FAR. FAR also has 60-foot launch rails, but we are not planning on using those. So here's our calculations for our shear and bending moments of the 2 stages together. These values are pretty similar to Encore from last year. Our safety factors are very high, so we don't believe there will be any issues prior to staging. We assumed a 10-degree angle of attack, and we still have very high safety factors for our fiberglass, carbon fiber, and our fasteners as well. As for our second stage, this is when things start to get a little dicey. As you can see, our safety factors are much lower. Our forces are about 2 to 3 times larger. And this is why we are going to implement a internal structure, because we do not trust our carbon fiber and our fiberglass to withstand those loads with those low safety factors.
I mean, think factor 12 still pretty, like, what is the like margin of error on load that, like, is that what's driving that, like, what's driving your low confidence in this thing? I think safety factor of 12 and 6 is still very high.
Oh, sorry. The question was, like, what's driving our concern, because our safety factors still look pretty high on our calculations, and that's not taking into account carbon fiber at supersonic speeds. And we know, like, carbon fiber can flutter at high speeds, so we're worried about like the structural integrity of that when it's going Mach 1, because we haven't sent our carbon fiber anything past Mach 0.9.
I'd also like to add that these safety factors are specifically for any bending moments, and we still have a lot of other significant calculations on the forces on the body tubes. This is just accounting for its bending moment and not other factors yet.
Yeah, are you planning on doing some sort of like combined loads analysis? It's like over CDR?
Yeah.
Okay.
Yeah, these were just initial numbers that we wanted to get first, especially because our rocket is so tall this year.
And then talking about the nose cone, Kendall did some thermal calculations and a sim of the aluminum tip at high speeds. And aluminum has a pretty high melting point, but we did have some concern. Her model isn't totally refined yet, but we don't think it will reach that stagnation temperature. The surface temp was calculated, I believe, at apogee, so that's why it seems low. She'll have to run that at max Q, because that is when the forces will be the highest, and that's probably when the aluminum tip will heat up the most. Okay, so Tim and I each individually did some calculations for the internal skeleton. And Tim, if you want to talk about it.
Sure. So for the internal skeleton, some of the biggest factors we looked into was like the Young's modulus of the rods and the what's it called, the exerted force on the actual body. From our research online, we couldn't really find Young's modulus given to us directly on many of the websites, so we did some research into some general values, and me and Calvin came up with values ranging between 200 and 230 gigapascals. And we also did for the exerted force on our body, not sure why that switched, we did it at max velocity and acceleration just to account for like the worst case scenario. I don't think in our models that actually happens. And our rods, we estimated we're going to take about 70 to 80% of that exerted force. And we both ran the calculations, and we came up with a diameter of 6 millimeters, which seemed on par with what the club did back with the other two-stage rocket, which I can't remember the name for. Ajax, thank you, Calvin.
And so just quick clarification here, like this is like stringers on the inside of your airframe. This is not like a separate structure. So like they will be bonded, will they be like bonded into the airframe? Or how are these rods going to like now? Like are they going to be like skin and stringer type analysis or
Here, I'll go to the next slide. I think that might help clarify.
Yeah, so at some points, like the recovery tube, they will be right on the body tube. But then for something like our avionics section, we thought it would be better if the rods would be separate from the body tube. So the rods are like 5 or 6 millimeters away from the body tube towards the inside, and then that goes on down into the motor mount as well. And the rationale for that was just because with the recovery section, that's like a pressure vessel, and we didn't want our rods to be compromised by that. But then because they are going to be on the edge, that means they're probably not going to support the carbon fiber as well because they're attached to the carbon fiber versus if they're totally separate, then they're going to be able to carry more of that load moving down. Yeah, so we're still planning on, we haven't figured out how to distribute the loads, but we do want to distribute them between both. Like the 2 prior years, we've relied entirely on the body tube and the couplers, and that's held up great. So we're confident in that up to Mach 0.9. But we are concerned about the supersonic speeds. So that's why we're trying to implement the skeleton to support it when it does go supersonic in case that the outer structure does fail. But we are not quite sure how we're going to like evenly distribute loads because like the rods are either going to take the load or the couplers and body tubes are going to. Tim, do you want to go into the design?
Yeah, so we for most of the skeleton, we're using 6 rods along the what's it called? The motor section here and the avionics section here, but we had to go down to 4 down here because of the space required for the fins. And those are all offset about in the slide a 1/4 inch away from the actual body tube. And the one exception of that is the recovery. Oh, sorry. This. Sorry, tech issue. The exception of that is the recovery section because we are going supersonic. We're trying to give recovery as much space for the parachute as possible. So those are actually going to be tangent and secured with, partially with epoxy to the actual body tube.
I guess so. Another question here is, where is the load from the motor actually being translated into the airframe? Is that going to be at the aft enclosure, or is the load going through the forward enclosure on the airframe?
I am not sure, being honest.
You said the load from the motor?
Yeah, so like where's the actual thrust from the motor reacted on the airframe?
Yeah, so like typically it's been just on our bottom bulkhead, and then by attaching those rods to these centering rings, we're hoping it will get translated upwards as well. But at the same time, we're worried about the forces coming down on the rocket because the drag forces will be very high.
And to add to that, the blue tube holding the motor casing is going to be epoxy to the centering ring. So it's mainly the centering rings and that bulkhead that are taking that force.
All right, so just to go a little bit deeper into the centering itself, I already mentioned we're going to go to 4 rods for the rings, for the 10 sections, sorry. And the rings are about 7.5 inches apart, and we have our, sorry for the people on Zoom, Teams, we have the separation plate here, which is also going to be our motor retention plate. And this ring right here is the one that's going to transition between 6 and 4, although we're looking into potentially changing that.
Yeah, and just to clarify a little bit more on the transition to the 4 rods, we did that because we're going to have 4 fins, and we have concerns about our fins also flying off because there's very little room between the exterior of the body tube and the motor mount tube. So by having these rods align with the fins, we're going to find ways to like either epoxy the fins to the rods or have a little more secure like bolt and fin type of thing to secure the fins to the rods themselves. And we think that's going to help our fins structurally as well. Yeah.
You consider doing a fin can for the bottom section instead of having them go through like by either laying them up with the actual body tube section or locking them into the body tube section somehow?
In terms of our fin retention and like how we're going to go about that, that is our next steps in terms of what we're going to do for CDR. we've considered a few ideas right now, but we're still uncertain which direction we want to go with.
Did you say do the layup like the body tube with the fin, like
But
directly?
you could add on top of, you do both of those layers, like a layer.
I see. That sounds difficult without the proper like mold and tools to do that. We only have like mandrel and plate.
Yeah, well, I mean, because you don't have to be like, you could just develop some sort of like jig to, because all you need to do is make sure that the fins are tangent to the body tube section. As long as you can have something that like can ensure that positioning, like all you're doing is applying like an epoxy fillet and then putting it over top of that. So you don't need to make it super complicated, but that can also just add rigidity to the outside. So you're not relying just on that, on like the epoxy that's going through the wall for all of the people out there.
Yeah, so from my understanding, like we typically do fillets on the outside, but you're saying like on top of those fillets, we have another layup going across the fin from the body.
Yeah, that's just gonna give you more rigidity.
Gotcha. I think we could do that.
To consider, yeah.
This is like bugging.
Yeah.
Okay. Here's our BOM so far. Our main cost is aluminum because aluminum is expensive when we're buying like entire stock, as opposed to tubes. So, as part of that, like our couplers are going to just be hollow with bulkheads, because that way we can just buy the aluminum round tube, which costs a lot less than the aluminum stock, than the round aluminum stock. And that way, if we need like any type of pressure vessel or we need separation within that coupler, we're just going to throw on a bulkhead externally.
Did you consider any other materials like Delrin, plastics or phenolics, instead of aluminum? And we cut down on cost.
We did not, but that's definitely something that we should consider. Also, Delrin's probably a lot lighter than aluminum, right? So that'll help.
Do we know how to work with that stuff? We know how to do all the aluminum.
We've done acrylics for an avionics section in the past for crescendo. Water jetting worked. Other plastics can be laser cut a lot easier.
Delrin's in the sheet. Oh, no, that's what makes it really good for applications like this. It's keeping the walls in operations and goes off.
Okay, yeah, that's a great way for us to cut down on costs because, yeah, our aluminum is expensive. That's it for our structure section. Does anyone have any additional questions on teams or person?
Yeah, this is Josh Van Schoik. I'm just curious, you have a lot of analysis shown here, which is great. Are you planning to do any actual structural testing to validate your models you have?
Yeah.
Well, first, that was not the end. There was more risk
next
concerns
section
and next steps. And then a whole section on all our different testings at the very end. But I'll let Calvin get back to it.
Yeah, so we have some next steps too. Sorry, I totally forgot about those. So yeah, as far as risks and concerns, from last year, we still haven't figured out a good way to get our holes 90 degrees apart on our couplers and bulkheads. So that's been an issue again. Like we used the 90-degree offset on the mill clamp and it wasn't 90 degrees. So finding a good way to do that, maybe just like 3D printing out a jig. The even distribution of our carbon fiber rods is going to be important because we are kind of worried about that 6 millimeter diameter, and like there's no way that we can account for the rods to take 100% of that load if like they had to. So making sure that the rods are evenly spaced, even in length as well, is going to be important for us. Safety factor of our internal skeleton, we don't currently have one. Our safety factor was just assuming that we have max velocity and max acceleration at the same time, which isn't going to happen. testing the strength of the internal skeleton, and then the natural frequency of our fins, because those will definitely flutter, and fin retention, which we mentioned, and budget as well, because we are running at a high budget right now. And yeah, going forward to our next steps, we're going to be doing a lot of testing, hopefully. So we already have carbon fiber layups that we're planning on testing in the next couple of weeks. Reaching out to Online Metals for looking at metal, looking at Delrin as well will be added to that. Creating a buckling analysis model, making a scale model of the internal skeleton once we get those rods as well. Finalizing our CAD and doing some bolt shear calculations, because our bolts will be bearing a lot of load as well, and a lot more than previous years. And then, yeah, with testing, we will, at the end of all of the sections, we will have an entire testing section as well. Any other questions?
Yeah, I was just wondering if you guys had a weight estimation for the internal skeleton, and then if the aerodynamics team accounted for that.
Yes, we have a weight estimation, and the aero team accounted for that. And it's, yeah.
Okay, what is it? Just curious.
We'll try to look that up right now. I think before we move on into our last few sections, we're gonna take a 10-minute break for everyone. And so while we take that break, we can get you those numbers.
Okay, thank you. And then also, I had a question. This is more the airframe side, but I guess you guys are planning on doing manufacturing the body tubes again yourselves, right?
Yeah.
Yeah. So I remember from last year, we were running low on like release film, and like I think breather layer maybe perhaps too. So from what my memory, So like, are you guys getting that donated again?
Yes, you are right. We were running low on that stuff. Anything that we don't have, we will be trying to get donated again. But one of the things that we are buying is that shrink wrap tape that we've been talking about for a while, Will, if you remember that. And that would mean that we wouldn't have to use so much release film. We wouldn't need vacuum bag anymore. We wouldn't need breather. Well, we could still use the breather, but like that's what would kind of ruin the surface finish. But yeah, the shrink wrap tape would help reduce that. And it was only about $50 for enough shrink wrap tape to last the whole year. So we figured that would be a good trade-off without instead of having to try and source all that other vacuum bag stuff.
Sorry, what was the shrink wrap tape again? That method?
Yeah. So it's basically, instead of putting the release film, breather, and vacuum bag, it's like a tape on, or that when it's heated up, it will compress and it'll like that's what's putting that like vacuum pressure on the part itself. It'll give us hopefully a much better surface finish, because when you use the breather, or that like kind of not quite smooth surface finish we've been getting on our body tubes, is because of that breather being pushed into it, and the breather itself is not smooth. The shrink wrap tape would be smooth, applying a constant pressure across the whole thing, giving us a better surface finish. And then also, like I said, we wouldn't need all the vacuum bag stuff anymore, because the heat shrinking it is what's causing that pressure and vacuum. That makes sense?
I see. Yeah. So would like, is the method for this, do you just wrap the whole entire body tube in this tape?
That is exactly the method, yes. It's not like exactly tacky tape, but on the ends there is like a special part that you use to like keep those sealed on the ends. And so you just wrap it all the way around and then seal it on the other end. And then you don't have to worry about the vacuum, and we don't have to worry about like epoxy getting sucked up into the vacuum, because there is no vacuum. The epoxy will all stay in inside that where the pressure is being applied, and then that epoxy will help that surface finish.
I see. Okay. And you're sure it would last like a whole entire year? Because it seems like wrapping the whole entire
Yes.
body tube. Okay,
So you only need one layer of it, and the $50 roll we bought, it's 2.5 inches and 300 feet long. And from some initial calculations, I think it would take about 20 feet to wrap the entire mandrel. Our body tubes, most of them are like substantially less than that. So with that 300 feet, it should last, or we do what, 10 body tubes, even with that 20, you're at 200. It should last the whole time.
got it. Okay. And sorry, so you wrap it around the outside, and
Yes.
then the mandrel between
The
the
inside.
part and then. Sorry, what was that?
Yeah, the inside release film, is that what you're talking about? It still does need release film on the inside. It's just now we
See.
only need one thing of release film each layup instead of two.
I see. And you guys are gonna use that release film that you already have, the agreed one.
Yes. Or source more. I don't think we can use that like quote unquote crunchy green one because there's not, or well, actually it might still be enough pressure, but we'd have to check. We're gonna do testing on that because we haven't used the tape before. So we're gonna do like test parts before we actually try. But yeah, the plan is to use the release film that we already have or try and get more donated. We did get some donated at the end of last year, but I'm not entirely sure if it's perforated or unperforated. And if it was perforated, we would not be able to use that. It should be unperforated, but when I looked, it didn't look unperforated. So they might have sent us the wrong one. But yeah, we still have to look into that. Yes.
Got it.
Does that
Okay.
answer?
Yes. Yeah. Thank you.
Will, did you also see we have the weight input in the chat?
Got it. Okay. Ethics.
Okay, if there are no more questions, we're gonna take a quick 10-minute break before moving on to the next few sections. A quick 5-minute break. Yeah. Resume at 11. All right, definitely should have been more prepared for this question. Thank you.
Thank you.
Just like.
I thought you showed it. Yeah.
It's just, yeah, but Joe. So that's all. If you could say small.
I figured that was it.
Yeah. Okay, everybody, it is 11. We will be moving on to the next sections, starting with recovery. Metzley. Oh. Yeah. We're gonna be starting, so quiet, please, or whisper at least. Sorry, Metzley, go ahead.
Okay, hi, I'm Metzley. I'll be talking about the recovery system. Okay. So first and foremost, I just want to talk about why I'm kind of just reusing the recovery design from last year and the year before. So it's the same recovery system we use for Encore and Crescendo. And there's like three main reasons why I decided to do this. First and foremost is cost has been like a really big issue this year. And if we reuse the same design, we have a lot of reusable parts we can use. So it'll save a lot on costs. Second of all, it's a pretty reliable system at this point. We've used it 2 years in a row pretty reliably, and in a rocket where there's a lot of unknowns because we've never done a two-stage before, it's pretty important to be able to mitigate a lot of things that can go wrong. And if we're using something we're familiar with, then things are less likely to go awry. And finally, it was just like really easy to adapt from a single stage rocket, which is what we've been doing, to a two-stage rocket. So there wasn't really any concerns about it being difficult to integrate into a two-stage, and it just has like minimal conflict with other systems. It's not a design that structures really has to worry too much about, or separation really has to worry too much about, or avionics has to worry too much about, because it's pretty easy to use. So what would this design be? Well, on the booster stage, you can see right here, it has a drogue chute, a main chute and its bag, a bottom coupler, peregrines, which kind of stick through the bottom coupler into the avionics tube. There are tender descenders that connect with the shock cord to that bottom coupler. The body tube is the main part there. There's a shock cord, and the top coupler, which on the booster stage is right on top of that top coupler, will be the separation system. So our recovery system is essentially right under that separation system. And then for the sustainer stage, it's kind of the same thing, except the top coupler now has the nose cone on top of it. There's no other system or whole other rocket on top of it. Okay, this is the outer profile for both the booster and the sustainer. They both kind of look the same. Essentially, what we're working with is a pressure vessel that'll be created from a carbon fiber body tube and aluminum couplers. There's going to be an interference bit between the couplers, bulkheads, and body tube. In the booster stage, like I said, the transition rests on the lid of the pressure vessel, and in the sustainer stage, it's a nose cone on top of it. There will be through holes on the bottom bulkheads. It's going to require 2 through holes, one for an eye bolt, which will be secured with a backing located in the center of each bulkhead, and this eye bolt is essentially what we're connecting the shock cord to. And then there's going to be one small hole that will allow wires to connect from avionics to our recovery parts, namely the tender descenders, because the tender descenders are not sticking through the bulkhead. It's only the peregrines that will be. It is. Tri-Aero? Okay. It does. Okay. So this is our first of our internal components. They're the CO2 peregrines. We'll be utilizing peregrines from Tinder Rocketry. They're going to be placed around the eye bolt, and like I said, they're going to be sticking through the bottom coupler. We're going to be using multiple for redundancy, probably using 2. So they're used to release the drogue chute at apogee. Essentially, what will happen is when avionics senses apogee, the CO2 will fill the pressure vessel. They're going to send a signal that'll set off the black powder in that charge cup. If you can see it there, there's a charge cup and there's black powder in there. It'll set it off, and that'll essentially puncture a hole in the CO2 canister, and that'll allow the CO2 to fill the pressure vessel, and the resulting pressure is going to pop off the top coupler, and that'll force out the drogue. As for the tender descenders, these we're also going to be using these from Tinder Rocketry. They're going to be placed in series and attached to the shock cord between the eye bolt and quick link. The point of these tender descenders is to essentially keep the main chute in the body tube until we want them to release, because the main chute is not supposed to go off until like 1,000 feet after the drogue chute goes off. So again, we're going to be using 2 of them per stage for redundancies. That's 4 tender descenders total. We already have 2 in the CPSS cage, so that saves us some money. Black powder within the tender descenders are going to cause the quick links to separate when we decide to release the main chute. And when those quick links separate, it'll essentially allow the shock cord to actually be freed from the O-ring and not the O-ring, the eye bolt, and that'll allow the main chute to actually be pulled out of this bag by the drogue.
That's in the 1,000 above the ground.
Is it? What's that? Above ground, my bad. 1,000 above ground. Okay, and then this is just internal components related to altimeters and other related avionics. They're going to be using an egg timer that'll be connected with CO2 canisters and programmed to sense zero velocity, which is our apogee. They'll be connected to the tender descenders and programmed to sense when we're 1,000 feet off the ground, not past apogee. And there's another avionics system they're making that'll just serve as the redundant system. We also have E-matches, which will be used to ignite the pyrotechnics, and those are going to connect from the tender descenders to and peregrines to avionics. Okay, so for some recovery calcs for the booster stage, we're going to be reusing our drogue chute and main parachute from last year. So that's a 36 diameter drogue chute and a 120 diameter main chute. We're also going to be reusing our shock cord, which is made of Kevlar. The velocity that we calculated using these parachutes is, or landing velocity using an apogee rockets equation, is about 14 feet per second, which is within or well below the 15 to 20 feet per second that's kind of recommended for landing velocity. I tested it to see if the weight were to increase by about 50%, if our landing velocity would still be safe, and it would be around 18 or 17 to 18 feet per second. And the open rocket simulation kind of agrees with these numbers, saying that our landing velocity would be about 14 feet per second. As for packing volume, we have more than enough space. We need like 260 cubic inches, and we have about double that amount. And then we also calculated drift. There is a drift of about 2,500 feet, which I think is pretty reasonable. That was assuming like 5 mile per hour winds.
What the aptitude for the booster stage is going to be.
Yeah, around 5,000 feet, more or less. Okay. For the sustainer stage, we will probably be using a 96 diameter main chute just because it is cheaper and it is more in stock. We're still going to be using the same kind of shock cord and the same kind of drogue chute. With the smaller parachute, we do have a slightly faster landing velocity. As you can see with the equation, we're getting about 21 feet per second, which is a little higher than the recommended 15 to 20, but not quite enough to be concerning. If the weight were to increase by about 20%, we'd be up at around 23 feet per second. The open rocket simulation seems to be giving a lot lower landing velocities, which is interesting. I'm not sure why. That might be a good or a bad thing, but it was giving around 16 feet per second. In terms of packing volume, we're also still fine. We need like 160 cubic inches, and we have, again, almost double that. Drift is a lot higher because obviously the rocket is going up a lot higher. The drift here is about 6,000 feet. I will say it might be one of the benefits of having a slightly higher landing velocity. The rocket will not drift as far because 6,000 feet is kind of a long distance to travel to recover the rocket.
Another question here, more for the structures team.
Mhm.
It looks like you have double the volume that you need for the recovery system.
Mhm.
Have you made that trade to shrink the volume of the recovery tubes to save some weight there?
So not exactly yet. The initial design when I was saying that like we were not sure about the volume, that was before a change was made with the coupler bulkhead. The way those used to be, if you remember, the pressure vessel was like in the middle of the bulkhead, that was the wall, or the middle of the coupler, that was the wall of the pressure vessel. But now, since we're only using the same coupler design and the bulkhead's on the bottom, it gained 2 inches on top and 2 inches on bottom volume space. So we could do that trade now to see if we can shrink that and see how that affects our weight and apogee. Yeah. But was that?
Yeah. But this might be more of a question for avionics people, but have you considered what happens if or do you expect your booster stage to possibly flip after separation? And what happens if that flipping occurs? Will your avionics prematurely actuate or deploy drogue when it's not supposed to?
Yeah, the answer to that.
The way that just off the top,
timers, but yeah.
The boost.
So the egg timers detect nose over, and I believe the way they do it is they detect the change crossing zero velocity. And then they wait about a second before they deploy. So we might have to, we might have to check with somebody to confirm that.
Email egg timer, Chris.
Yeah, we can email that. I mean, the way that we would be doing it in our redundant system would work that way. And, but yeah, that's, again, that's our backup. So for the egg timer, I think we should email egg timer Chris, but off the top of my head, I don't think that would immediately be positive.
Okay, yeah, I don't recall either how the egg timer do it, if it's purely altitude or if it's also a accelerometer to sleep it.
That's what they, on the little documentation that's on the website, it says that it deploys the drone chute at nose over, or a second after nose over.
Okay.
So I'll have to get specifics about how that's actually detected. Actually, it's crossing the velocity.
And question for you guys is, how comfortable are you? What are those like safety margins on, will your parachute tear if it flips over and then happens?
The question was, what are the, how comfortable are we with the safety margins in case the parachute tears or if the thing flips over prematurely?
If it flips over premature, like the booster stage?
Flips over prematurely and you have your drone deploys early. What happens?
Then first and foremost, probably snatch forces would come into play if it goes off early, which might be problematic. I haven't done calculation of snatch forces, 'cause I kind of assume it goes off at apogee, but snatch forces I wouldn't be too worried about because we have a pretty strong shock cord. In terms of the parachute ripping, if it happens in booster stage, I wouldn't be worried about it because booster stage is kind of slow. I don't think it would rip. And even if the drogue chute did rip, I have faith that the main chute would probably be able to slow it down enough to where the rocket doesn't get completely destroyed. Have anything else?
Yeah, no, if it were flipping and it deployed, there is a good chance that when that parachute is pulled out, based off like all the loads and the wind, it will probably totally shred that parachute. In terms of how the first thing would be how do we avoid that? That'd be our best mitigation. Yeah, we could hope that when the main chute is deployed, that it does slow it down. It won't slow it down to where it might not not get damaged when it hits the ground, but there's a good chance we're 1,000 feet up. It did drop 4,000 feet, but hopefully it's going to be enough. That's something we need to look into and a worry that we have, especially in terms of the parachute on the sustainer, because that's the one that's going to be high and there's a good chance of those forces not being kind to our parachute.
We could also look into figuring out how to, instead of the transition, it could be like a false nose cone that'll essentially turn that booster into its own rocket that'll hold its own stability like alone rather than, or so that would kind of mitigate those forces or causing it to like flip and spiral and do whatever it wants. If it was like its own stable structure, that would help.
Yes.
Just work out, no. Right, so she's behind it one second. You know, I have actually, opportunity, so which.
It's a point on mission.
Okay.
Okay, yeah, for the people who probably couldn't hear that, the egg timer is based on apogee, not the velocity, so it should be 1 second after reaching apogee.
Yeah.
Is that right?
We should check whether the egg timer considers orientation in its consideration of altitude. If it's maybe it flips. I would expect that because
It's a barometer, so it's
right. Yeah, so I think we're okay.
The egg timer is a barometer, so we do not need to worry about like orientation being an issue and getting in like false negative apogee or like decreasing apogee when it since it's based on pressure.
Anything? Okay. So this is just like a very brief material analysis. We're just gonna keep using Kevlar shock cores. They're stronger than nylon. They're lightweight. They don't have they have a lower stretch, but if you wanted them to be a bit stretchier for like improved shock absorption, you just make them longer. They're flexible and easy to handle, not like unlike wires or anything weird like that. We're gonna stick with Fruity Shoots and their ripstop nylon. Again, they're lightweight because it's ripstop. It'll resist tearing and abrasions better than just like standard nylon parachutes. They're elastic, they'll absorb shock. And Fruity Shoots in particular, they have a very high coefficient of drag at like 2.2. So Fruity Shoots parachutes in particular are like just a really good design and material to go with. All right, this is our bill of materials. Like I said, the whole point of reusing the recovery system from last year was to save on material costs. So you'll see that on here, there's like a quantity total and then like a quantity needed. For some of the stuff, we don't even have to buy it because we already have the stuff in the cage. So the total cost, like accounting for things we already have, is about $850. The points of concern, like we were talking about earlier, the supersonic effects of parachutes are our biggest concern. Parachutes on like supersonic rockets tend to have a higher tendency to rip, especially if something goes wrong. It's not going to be withstanding those forces going at those high speeds. I'm not entirely sure if like the tendency of parachutes to rip is caused by just improperly timed deployment factors, like some weird stuff that has to do with the changes in air pressure or the changes in like the forces that occur when you're going that fast. But we are gonna have to try to see if we can get more research on that. Hopefully it's just improperly timed parachute deployment, because if so, we can work around that. Zip ring's another slight issue. Again, if the recovery system deployment is improperly timed, then the Kevlar shock cord can do some major damage to our body tube. And again, this will be enhanced if it occurs during the sustainer stage specifically because of how fast it's going. And then there's just some slight concerns with integration. I am a little worried about still how separation might impact the pressure vessel, just because separation is still being developed a bit, and it has all the rods and stuff, and it's just right on top of us. And we just want to make sure there's no interference between the two. And weight changes might also be a slight problem because, as you would recall, we're already going kind of fast for the landing velocity for the sustainer stage. And if that weight changes to be like more than 20% higher, like 50% higher, for example, I'm not sure I'd be comfortable with the landing velocity. And at that point, we'd have to start thinking about changing parachutes and readjusting like how much space we need in the tube and all that stuff. Next steps, we'll need pressure vessel calculations, just check for shearing and check for pressure, failure checks in the pressure vessel walls. Carbon fiber is pretty strong, and historically we've had like a really high safety factor with that stuff. So it's really just verifying that and making sure. The more important part is just seeing how much CO2 we need to pop off the pressure vessel lid. I'm expecting like 2 12-gram or just a single 12-gram canister will be enough, but it's good to get those numbers and confirm it. Then we're going to examine our peregrine itinerary assessor parts, just make sure we know how many more parts we need, and or like if we need more parts and how many more are needed. We need to update the CAD models accordingly and prepare testing procedure documents, because there's going to be like 3 tests for recovery down the line.
Kind of a question both for avionics and for recovery. Have you thought of any contingency plans if like either booster step or stage step, or like nose cone step or stage step doesn't occur? Like, will your avionics know not to fire the second stage motor if you don't hit stage step, or will you just blow a Yeah, that's what I would be worried about too. If for some reason, like either friction or something that doesn't cause stage step to happen, and what the consequence of it would be.
Would it be safer to blow a hole in the booster so that you could possibly recover the upper stage?
So
Is that parachute size to both?
I believe so. Once I think the separation and the recovery are different systems, if I'm not mistaken. So the failure of the separation would not cause a direct failure of recovery, as long as we can sustain a hot fire separation of just blasting straight into our separation plate that will be talked about, which is one of our redundancies for separation. It is held on right now by like shear pin. It'll be talked about just in a moment. But yeah, it is essentially two different things that are happening. So the recovery would not be directly influenced by that, is the goal.
And then kind of a follow-on question is, are you gonna have any fail safes for if it doesn't separate, do you just have this pressure vessel, or are you gonna have any leaks or just like an orifice on the pressure vessel itself to feed out that pressure? I would recommend that so you don't accidentally like crash with a, 200 PSI or however, I don't know how much it's gonna fill up with. But reduce your explosive energy potential in off case you have a business recovery.
We usually do drill some small holes in it. We have traditionally for the past few years. We also have that hole for the tender descenders, so some gas can escape from there as well. So hopefully that'll calm it down a little bit.
And that can be a pretty simple calculation too.
Yeah.
Like if you have your starting pressure, you have a squared like orifice, you can calculate if you want to bleed out on all of your pressure in the like 10 seconds or whatever that escapes consistent recovery. You can have them all empty.
The question was if we considered releasing pressure in the case of a ballistic recovery, so we are not dropping a pressure vessel from thousands of feet up. And the answer was that there are essentially holes that should hopefully allow the pressure to release, and we can do calculations to make sure that it will release by the time it reaches the ground.
Yes. 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 Mhm.
Any intentions, like the testing to to make sure that the water is still there, like lower than someone that or to use like use the use, but just to make sure that it is still suitable to be able this one.
Yeah.
The exact shock cord, we can buy more.
Yeah, we can
Uh,
buy more.
The exact shock cord, it might have been misleading, but we do buy more shock cord. It's just like the parachutes are being reused, and we could do the same thing, make sure the parachutes are still.
Yeah.
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 Yeah, that is a good point to bring up.
If you're using parts, make sure that you can't have everybody very full. Or that's not good.
Furthermore, do we know what the shelf life of the Kevlar is, and you know how old our Kevlar is? I don't know about Kevlar right now for like climbing rope and stuff. You're supposed to only use soft stuff for like 5 years and it expires.
Didn't we buy a shock cord last year?
I think we bought it 2 years ago.
Crescendo, but we could check into the shelf life.
It's also not that expensive if we have to buy. It's like $20 for like 50 feet or something. Yeah, so it's not that big of a concern.
Yeah, the questions and comments were about like what the state of our shock cord and recovery stuff is and making sure that that's still good, and also what the shelf life of the cords may be. And we believe that it's still within that shelf life, but if not, we can always buy more because it's relatively cheap compared to other stuff on the bill of materials.
Okay, good. Okay. So next is separations. So, hello, I'm in charge of, I'm Tiana. And I'm in charge of stage separation. And I'll be walking you through the design process. Okay, so our main objective is to design a mechanism that separates the two stages in a reliable and controlled manner. For that reason, we decided to use an explosive. We decided that an explosive release would be the most reliable and realistic or feasible solution with shear pins holding the two plates together. As you can see, the top plate is that will be connected to the second stage, and the bottom plate will be connected to the first stage through structure rods, which are not shown, but will be incorporated into the CAD later on. What is not also, well, actually, okay, so to begin, how it works is basically by explosive release, I mean that we will have black powder sitting in the reservoir on the bottom plane, figure 4.3, the lower half. And so the top plate will come down and is connected by shear pins. And once that charge of black powder, once it's the explosion happens, the shear pins will break and the two stages will separate. What's also not shown in the CAD currently are inlets for the charge and grooves for wiring that will send the signal to split the black powder.
Quick
Yes.
question here.
Mhm.
I take it that the upper ring, like is not gonna sit, so in that kind of room on the lower, that's
Yeah.
where black powder sits. And then there's a gap between that upper.
Yeah,
and lower,
so there's gonna be a gap in 4.2. I didn't like put it all the way. It's going to be flush, the two, well, not like the top half. That's also for reasoning of stability, which I will go into in the next slide. So some points of concern that we have are signal malfunction for the black powder from avionics. Or the black powder, well, and or the black powder becoming inert from foreign substances or like water that will discharge it. And shear pins causing a moment or causing the rocket to rotate are also a big concern. Other design considerations that we had for in the process of this design were explosive and mechanical release, which could be black powder with a latch release. And basically a latch would act as a more controlled shear pin so that the chances of a moment being caused would be significantly lessened or reduced. But in the design process, we figured that this is, so sometimes, well, the more complex you make a design, it's like trying to reinvent the wheel. You don't want to reinvent the wheel, so sometimes going with simpler solutions and then moving to more complex is better, especially in our case of budget. And then also we had an idea with black powder in a gas spring system, which is a passive system that would push the lower half, or well, yeah, the lower half and the upper half apart. Any questions?
And one thing before, you don't stay, just the cost for that, we don't have a bill of materials there because the stock that we'd use to make those little rings or plates is included in the structures bill of material for their mantle, or not mantle, their stock.
So that's the same 5-inch diameter.
Yeah.
Once they are printed.
Yes, 5-inch diameter. That upper one is like the retention plate as well. The other one is attached to the transition with just bolts like we usually do.
Okay, and then I have another question too, with what is that, if you go back to the CAD,
Mhm.
like what's the purpose of that like center in that's on the lower device?
Oh, yeah.
Or is that just a shear mechanism for preventing between the stages?
Yeah, so sorry, I totally forgot about that. So basically, in the case that, given we don't know the winds and what angle the rocket is going to be at when separating, exactly, it could be perfectly straight or it could be 10, 15 degrees. I was thinking that in a way of like aligning it to make sure that it wouldn't just rotate straight off, because you have just two stages and it's basically it'll just help stabilize the higher up it sits. So, but we also do have a constraint with the motor from the second stage.
Yeah, I would definitely talk with the load speeds,
Mhm.
kind of like what this year you're expecting.
Yeah.
Because I'm sure you can shave a lot of weight off of that, especially like looking at the lower, like, I don't know how much is that whole thing's gonna be solid looking at the low.
So it is currently, but
Production.
yeah, I'm gonna do an FEA analysis of weight reduction and see where I can like shell out material so that it's less heavy and still structurally.
Yeah, I think you're right. The plug probably could be shrunk a little bit. Depending on those calculations.
Yeah, no, I would think make it like a ring instead of making a solid.
Like a Lego set.
So.
Do you all know if you aren't able to get the upper stage onto the lawn trail with a pin? I can't remember the names of those. Will this be able to hold the upper stage horizontal?
Yeah, without rail buttons, Calvin is nodding his head. He is saying, yes, it would be able to hold.
Cool.
He's the structures guy.
Awesome.
Do you have more to add to that, Calvin?
I mean, I hope so.
Never mind, he's not that confident, then we will do extra analysis on that. Yeah, so we can look into that and, yeah, we'll look more into that then. Thank you for bringing that up.
And based off a few of the papers that we've gone through, at this point where they separate, you should be able to hold the rocket and it not like completely break apart. So it'll have to make sure, like we have to make sure that like it can't hold it together. And there's our way so that we can test that.
Yes, I would imagine putting it horizontal and adding weights roughly of the rocket size would kind of help with it, or like adding like a moment
Mhm.
of that expected like static weight, I guess, would help give us an estimate of able to survive that without actually having the entire rocket built. And then we can redesign if it doesn't account for that.
Yeah, excellent. Just want to make sure y'all are considering it.
Cool, thank you.
Any more questions? And on to avionics.
All right, I'm Jack Ryan, the avionics lead, and this is Spundin, who is the software lead for avionics as well. And yeah, we'll be talking about our avionics system. So our main PCB that is going on the two-stage rocket will be the telemetry operations manager, or TOM for short. And TOM is basically meant to be a one-stop shop for all of your avionics needs, right? So it has all of your basic avionics sensors like your altimeters, IMUs, GPS, and it's meant to handle all of the readings, the filtering that you need to do, and as well as communicate that down to ground station. And it has a lot of power regulation on board too, so that you can provide it with a wide range of voltages. You can use pretty much any reasonable battery and it should be able to run. And it also has an additional third microcontroller that is left intentionally as a blank canvas to do whatever else you need it to do. And it has a lot of GPIO and that sort of thing so that whatever mission it's needed on, it can accomplish that. So here's a little black box diagram of TOM. So you have your main power stage, which you have your battery input. This battery can technically be anywhere from around 9. Although we used linear regulators, so we definitely want to keep that lower. And we plan on some point probably adding a boost converter so that we are not losing so much power to heat on board TOM. But so you have 5-volt regulators that maintain a constant 5 volts, and then 3.3 volt regulators for all of your logic level devices. And so there's 3 main microcontrollers on board.
The first one is the sensor microcontroller, which we call NAV, and it has 3 IMUs, 3 altimeters, and a GPS. And next is the telemetry microcontroller, which we call TLM. And so this has the LoRa module, which is probably the most important thing that it handles. And it also has flash memory for storing information about the flight in case our telemetry fails or we have gaps or something to that effect. And it also has an ADC to monitor the battery voltage so that we can send that out throughout or after the flight if need be. And then finally, we have the MPU, which is the main processing unit. It's that blank canvas that I was just talking about. And essentially, it's an STM32 that just has a bunch of exposed GPIO pins, lots of general purpose pins, as well as some specialized I2C, SPI, and UART ports. So basically, whatever you need to connect to it, you can. That's the idea. And I forgot to put it here, but these 3 microcontrollers all communicate through a shared CAN bus. So that's how they share their information back and forth. So we have a couple of redundancies in case some things don't work. So as mentioned in the recovery section, the main device that we'll be using for recovery is the FAR-approved egg timer quark. And as we discussed earlier, it deploys the sorry, not primary. That's the drogue chute at nose over, and it detects that based on a negative velocity for more than 1 second. However, we also have pyro channels that can be used as well if the egg timer fails, and can be used for separation also. Additionally, as you might be able to see on the board here, along the side we have a lot of connectors. And this is, we routed out a lot of the communication ports for the sensor microcontroller so that, in case the sensor fails or something on board doesn't work, we can always plug in another breakout board or an off-the-shelf component to replace it. So there's some I2C and UART ports available for backups. And then in terms of sensor redundancies, we have, as I mentioned, 3 IMUs and 3 altimeters. And the reason we like 3 is that we can take the median value rather than the average, because if we take the average value and then one of them fails and, for instance, starts reading zeros, then we divide our actual value by half. And this was suggested last year to us at PDR, so we decided to run with it this year as well. And these will be these values can be fed into a common filter for increased accuracy. And then, as I mentioned, we have 4 pyro channels on board, and these are pretty simple. I have the schematic up there on your right, and basically all it is the GPIO, 4 of the GPIO pins from the main processing unit. Their GPIO pin feeds into an operational amplifier that amplifies the 3.3 volt output to 4.5, which is the on voltage of the MOSFETs. And so this drives the gates of the MOSFETs, which allow the high current to pass through. And what you see from this simulation is it's just a SPICE simulation of what we expect to see. So the 1 ohm resistors at the bottom are meant to represent the small load that we'll get for a brief moment from the black charges, or from the black powder charges, right? And then we simulated sending a 3.3 volt pulse, and that's amplified to 4.5. And then it's a little bit hard to see, but the blue line is the current that goes through, and we can see that it allows a peak of up to 3 amps, which is more than we should expect to see, I believe. And then it also pulls this current from a separate 5 volt regulator from what goes into all of the logic level controls. So this is meant to prevent brownout because it's coming from a different regulator. Another thing to mention is that while it's not shown in this schematic, on the actual board, there's pull down resistors as well on the GPIO pins. And this is to make sure that you know, if one of them is left unprogrammed in its high impedance state, that we don't accidentally turn them on. So it sets the default value to off until we explicitly drive it high. So that's just another safety feature that we have on there as well. And we plan on testing these with recovery and separation in the future to make sure that these actually can work as redundancies.
Yeah, so in terms of software, we're aiming for two major milestones. Milestone 1 is just our sort of minimum viable product running on Tom. ESP32s support programming via the basic Arduino framework. So the goal will just be to get all of the onboard IMUs and like the onboard IMUs, altimeters, and the GPS functioning. And in the event that we don't have an SMD that we expected to work working, we'll use Tom's GPIO pins to just drive like breakout boards. And we're aiming to transmit from the onboard LoRa module. Also, if that doesn't work out in the sense that like our SMD components have some problems, we'll be able to use GPIO pins to transmit. And then ground station is just receiving via a Raspberry Pi using a basic script printing out to a shell. Milestone 2 is going to be more of a polished Zephyr system. So as soon as we achieve milestone 1 and sort of secure our minimum viable product for launch, we'll aim to move over to the Zephyr real-time operating system, kind of clean things up a little bit, include, well, we'll find like analogous libraries to the Arduino libraries that we use to run the basic sensors on the ESPs running the Arduino framework. And then we'll take other polishing steps, like maybe accounting for like data packetization, quality of service, and I guess making this more of a product that we can take into future years. And then we'll start using OpenMCT or Foxglove Studio or some alternative to display ground station data in a more polished way.
All right, and then so a few risks and concerns that we have, at least on the hardware side, is one, as I mentioned, I use linear regulators exclusively, somewhat naively, and those tend to convert a lot of power into a lot of heat. And so especially if we are running this directly from a higher voltage source, we have to test it and make sure that it's not going to overheat, you know, especially at far, it can get pretty hot. So that's one concern we have. Additionally, especially for a two-stage rocket, we anticipate that the vibrations will be a lot higher than we are used to. And so we would like to have a way of staking our components down to the board to make sure that they don't vibrate off, because that would be quite unfortunate. And then one problem that we've had in the past is with our RF components. Last year, we lost telemetry right on the launch pad. So we want to make sure that this year we do lots of testing and range testing to make sure that our antennas are actually going to work and that we can rely on them once it's time for launch.
Matthew. Speaking of vibration, it's kind of more of a question for the structures team. Have you done any kind of dynamic analysis of the rocket and the kind of dynamic environment that it's going to see like what vibrational load you're going to be expecting to see if the avionics team can like design that, or if that isn't something that you're going to look into?
We did find out that we have a vibe table that we didn't know about, so we might try and see if we can get that working, or probably contact someone in the ME department if they have a vibe table.
Yeah.
That would be good to set.
Yeah, but this kind of goes back, like, if sure it's good that you put it on a vibe table, but like if you don't know what dynamic environment that it's going to see in flight, not necessarily going to be as representative example. And that's, I guess, this kind of goes back to, especially with the like the rod, something some like high dynamic, you can see some high sensitivity on the rods, which could be just tracking. I think, and I can see that happening with one play, but you would have to run analysis and make sure.
We'll definitely add that to the list of next steps. Thank you. That is a good consideration.
And then last, I have the bill of materials for avionics. So the parts for each Tom board is about $150 for all of the components that go on the board, including all the sensors, microcontrollers, GPS, and such things. and we need 2 of them, 1 for each stage. One thing I forgot to mention as well is that the telemetry microcontroller also is equipped with Bluetooth. It's an ESP32, so it's meant for Bluetooth. It has an onboard 2.4 gigahertz antenna, and so if we need to communicate between the 2 stages, that's one way that we can do it without passing wires through, something that's going to be separated. Anyways, so this is the expected cost, and it's worth noting that we do have some of these parts available for the second iteration from a dev board that we didn't build in the past but intended to. So the second price, the price for the second set of DigiKey parts may be a little bit lower. And the price for 5 boards was about $50, and so we have all of the boards that we should need. However, we plan on also at least getting a backup GPS, which tends to run us about $30, and we need a very beefy 12-volt battery for both this project, and we intend to use it on the air brakes project as well. So, yeah.
So I guess another question here is, you can you're on the first stage.
We would like to have telemetry from both stages. So, and we definitely want at least to have GPS so that we can recover it. That was the thinking there. And so we might be able to get away with, not having all of the components, like for instance, not having the STM32 and maybe just doing the redundant pyro channels from one of the ESP32s, one of the other microcontrollers. We could maybe get away with that, but we do at least we want to have some form of flight controller on 2 stages. Yes, recovering GPS. Yeah.
Oh, and the separation, the thing that sends the separation is from the upper stage.
Any other questions?
Do y'all have a rough estimate of like how much power everything is going to draw altogether and how long the battery can run everything for?
Yeah, so the battery that we have or that we plan on getting is 5,200 milliamp hours. I don't have an exact estimate because based on how, computationally expensive everything is, the microcontrollers can go from, 50 milliamps to some of them, like STM32 can take like 500. But we also have the ability to turn them off with the telemetry microcontroller. And in that case, I would estimate probably in the 100 to 200 milliamp range. But again, because of the linear regulators, a lot of the power that we'd be using for that 3.3 volts would be lost in heat. So as of right now, I don't have a good estimate, but.
Okay, yeah, I'm just thinking you'll want it to run for like at least half an hour, if not an hour, to make sure it's still running by the time you get ready or have it set up on the launch pad and actually have the launch go off.
Yeah. So that was part of the thinking with our battery as well. It's a little bit overkill in terms of how much power we have. But yeah, definitely getting a good estimate once everything is powered on is a big next step for us.
I'd say
Sounds
more than half an hour. If it takes you a while to get a lock on the GPS on the ground, you might want like an hour or 2.
Yeah.
I think he said half hour on the launch pad.
Oh, sure, yeah.
I think that's also what FAR gives you for.
Yes.
So.
All right. Okay. That's it from us. Next up, we have testing.
Hello, my name is Ariel. Because we're doing so many tests this year, we wanted to kind of group them in a separate section at the end, so then we can say like what tests each subsystem is going to do. I'm going to be working very closely with each subsystem to develop their tests and then perform them, and just so they have a little bit more help, and then so we can develop some more procedures and get them checked, obviously. So we have our composites testing. Our current composites are out of spec donated material. So
So we need to verify that these materials are going to withstand the floats during flight. We did this last year with our material that the oven broke or the freezer broke down. And turns out they did not withstand the stresses anymore. So we had to get new material, which is why we now have out of spec material, but is new and still works for us since those tolerances are so tight for companies and industry. So last year we used an Instron, and we will again be using an Instron, and you're trying to find one that goes past the amount that Peyton currently has. This is an example of what they look like, and that is an example of testing. I don't know if Ryan can speak more on it because he did the test last year, but.
Yeah, essentially, so we did the 2 sets of tests first with that. Over the summer, the freezer broke and our composites were sitting or they were sitting at room temperature, basically.
Pain. Okay.
Yeah, so the freezer broke and the composites were sitting at room temperature essentially for like the summer. And when we came back and did the layup and tested, it was not great. So we got more donated that was extra from SpaceX that was out of SpaceX's like out of spec. But for us, like we're not going to space, so we don't need it to be that good. So we're okay with this like out of spec donated material. We tested it again, the numbers were a lot better. And just through like visible inspection, it was very clear that this was like stronger than others. This also helps us like test layer thicknesses, ply, the amount of ply that we need, so that, sorry, there's a group meeting going on right now. Yeah, it checks, we can use this to test how many plies. It would be, but then we'd mute Will and everybody out.
You just have to know tradition. You have to stir.
Yeah.
If you get another message, you put like
The 3 dots. Yes. That shows up. Get ready to click. Sorry, I am now distracted. What was I saying? Yeah, we can use that to check like the thicknesses. We have test articles that we just made of roughly the same height, different thicknesses or different ply counts, and the varying 5-6 inch diameter, and we're going to test those soon to see how they compare to last year's strain stress plots. And then you can click the arrow.
Skip structures.
Sorry, structure.
So for structures testing, we want to make sure that the body tubes on the Instron are going to withstand the loads with and without the skeleton. What we want to test here is how strong is the skeleton compared to not using one. We also want to test our screws. One of our biggest calculations is doing shear for the bolts, and then also just tensile loads. And we also want to get in touch with CalPAC this year because they have access to a bunch of different distribution testing machines, like the one shown right there, which are pretty cool. And things we don't have at Cal Poly, or I mean, just in our aero facilities. We also want to reach out to Online Metals for discounted metal because that is one of our biggest costs. Focus.
Go to notification settings. That's too much work.
So for our recovery testing, we've done these tests for 2 years now. But for our peregrine testing, we're just gonna weave it into our pressure vessel testing since we've tested them individually, as you can see. This is a working peregrine. And so for our pressure vessel testing, we want to ensure that the top coupler is going to successfully separate from the body tube in a safe manner. You want to combine with the avionics system so that they're going to test their system while we're testing our system. This is going to be probably right near when we're going to launch, but probably like a month in advance, hopefully. So most of our stuff's going to be set up and manufactured at this point. It's really just going to be a big test of multiple systems. And then we're also going to do tender descender testing, which is just ensuring that the quick links of the tender descenders successfully detach from the housing. This can also be used to teach other younger students, since a lot of us have done this before. But it's a cool test to watch
And it's just checking to make sure our tender descenders are still in good condition. And so for our next steps, obviously we want to do safety procedures, and then brief everyone on black powder, because those are specific, that's specific documentation that you need to learn. So for separation, this is our biggest test and probably our most dangerous test for our 2-stage, because it's basically a ring of black powder. And we've never tested this much black powder probably in a while. I don't know about before COVID, but yeah, for our group, yeah. And we need to basically make sure that the separation system separates and does not fail. And we can't test our hot staging as our redundancy, because that's just going to be the motor, but we can test black powder easily in our Cal Poly propulsion lab. So the test right now, what I'm thinking is just finding some way to secure the transition piece on the ground. That's going to be bolted into the separation with shear pins, and then all the pieces are going to be in there with the black powder. And then if the top just pops off, then we're good, successfully separated. Figuring out how to apply loads to that will also be something that we're looking into in the future. Yeah. Okay. So for some next steps, we have to obtain more black powder if we want to make a ring of black powder. Cody has previously offered us to get this for us somehow. But we're gonna work with him and Dr. DeTuris to ensure a safe test. Yeah.
Black powder pond.
Exactly.
But it's free, right?
Yeah. He said he can get it for us on a farm in Wyoming. But yeah, then we're gonna draft our testing procedures to ensure his black powder is safe. And yes. What was your question?
You have like off-nominal tests planned for this mechanism. I can see that like if it was to cock quite a bit before separation and you had the vibrations sucking all of your black powder to like one side, that it might have a weird load that gets stuck. Is there off-nominal test plan for that?
That's a good idea. We should definitely add those. Yeah, probably 2 or 3 years. Develop, but I think that'd be a really good idea, and just figuring out a way to mount it different directions.
Because this is our newest system, we're gonna test this multiple times. It's not just gonna be one test. And for CDR, we're gonna make our manufacturing and testing schedule, but this will be our first priority to make sure that any flaws occur in winter quarter, so we have all of spring quarter to fix them before launch.
So for our avionics testing, one of the big things we want to test is our combination with structures. There's going to be a bunch of rods in the avionics body tube, so we want to make sure that those carbon fiber rods are not going to affect the signal at all. Because usually we use fiberglass as the body tube for avionics because of this bad connection, but we're going to have rods in there this time, so we want to see, like, is a rod the same as a body tube? Is it still going to travel? Should we still get signal? So that sort of thing. And then we want to see, just assemble a stack, maybe have someone drive a short distance away and see if the other person still receives a signal. Another way we can test this is our air brakes launch, but I guess we're not going to use the rods for that. But for our telemetry test, we can use our air brakes launch to test this in January. But for our telemetry test, we haven't had telemetry for the past few years. So we want some way to track so we don't have to just search in the desert. But just assembling the stack again and driving out to a remote location to mimic FAR conditions, because FAR also is kind of an anomaly where you just lose signal, which is weird. But it's just a thing that happens to a lot of rocketry people. But we want to determine if our data collection is going to be successful in the desert. So then we can more easily find our rocket. Yeah.
The backup, if it does not go through the signal, or the signals do not go through carbon fiber, is to figure out a way to have an external antenna that's just like attached to the body tube or maybe the fin. Okay, so project budget estimates, as you can see, we are over budget. Let's go. Yes. Okay, thanks. Remember that and we'll write it down later. So budgets, aerodynamics. I did not, when we were allotting the budget, I did not account for the fact that we did not have the casing for the motor for the upper one. We have, or so that budget was only the grain. The casing alone is another 1,000. That's what's causing that to be up. We're not exactly sure how to get around that, other than just sourcing from somewhere else who's not making us pay 1,000. Yeah.
Are you sure in the closet of
Yeah.
curiosities, there's not any other motors?
So
Or there was quite a few that came.
we checked, and apparently there was one that was the right size, but it was cut off. I don't know why that would have been done, but it is not usable in that state. We were also looking for the little caps, because that would save us a couple $100. Those alone are like a couple hundred. Couldn't find any of those either.
Couple in there that have been melted through and.
Yeah, so the only one left is the M1939 one that I would like to reuse, so we don't have to spend another 1,000 on one of those. We thought about that also. They look like they could be made, but I do not know how much we want to rely on handmade things for that, because that is the big explosive, most dangerous thing. And if we don't make that right, that sounds like dangerous. But we can look into that depending on how this cost goes out. That is a good thing to consider. Exactly, yes. But right now we're looking into just different websites who sell motor and motor parts. Those are the values from like straight from Aerotech suppliers. There are some less reliable people that we could buy it from, but like they do sell. It's just like a store in like another state, just like a small store or whatever. Like they have motor stuff. We could buy it from them instead of buying it straight from Aerotech. Structures, we were expecting that to be pretty high. It was a little higher. Stock is the issue, but like Calvin said, they do have General Atomic stock in the hangar that seems up for grabs. If we could use that, that saves us about $600 on the stock, and that would help us reduce that budget by quite a bit. Recovery, I don't have much to say there. That sounds about right. Yeah, separation is included in the structured bond because we don't have to pay for that black powder, and we don't have to pay for the E-matches we already have. We don't have to pay for the stock if we get it from General Atomics stock supply. Avionics is wrong because I forgot to account for the battery GPS stuff. I was only thinking of the flight boards, so that should be 400 instead of 300. But yeah, take off that like $600 and you're at 4,650. And there's also we applied for a MEDAC proposal, which is from the mechanical engineering department. They give funds to certain projects. And we might be able to get a little bit of money from that. There was some complications with the stock. We're not allowed to buy stock with that money, but we had a little bit of other stuff on there that wasn't stock. So yeah, we're looking into ways to reduce cost. Yes, this is our last slide. Are there any questions overall? You don't need. Yes.
Are they based on like a?
It's just like, well, I had to put some other, but one. I doesn't know the knowledge of that names, but I'm pretty sure lots of just that. So is that, or is there anything about that thing that making the long or actively? But it's just another question. the answer right now. There's not, there's not provide that, if you're. It's, you start putting a lot of pressure. So is that, will that, continues to.
That is external pressure, right? They come here, on the inside of your body too. I'm also not aerodynamics at all. So my thought is that you have a hole, right? You cut in the body tube that equalizes the pressure. But I don't know, you'd have to have your aerodynamics people looking at what that is to inside the body.
Yes, we will consider that. That is a good point. Did not think about that.
Know more about that? Okay.
Well, are you big aerodynamics guy?
Yeah.
Well,
Will, are you with us?
Which Will?
Hey.
Oh. Yeah, so
Oh,
the
are you guys
question,
talking about?
we're talking about, it was just put in the chat, but somebody brought up the fact that the pressure changes once you hit like Mach 1 might confuse the barometer in the egg timer and might cause premature recovery. Do you have any thoughts on that at all?
Oh, I think, well, the egg timer isn't it set off? What sets it off again, right? It senses a negative velocity, right?
No, sorry.
Not by the barometer.
It says it off. The barometer acts as an altimeter, and it's based on the altitude. So once it reaches that peak altitude and starts dropping for over a second, then it will activate. But if at Mach 1, weird things with pressure start happening. I don't know. We're asking more like what the behavior of the pressures at Mach 1, could it possibly confuse the barometer?
Where is the barometer located?
Inside the rocket.
Huh. Yeah. Like off the top of my head, might be some weird behavior because, right, the shock before and after the pressure, you're gonna experience a pressure drop. But, yeah, that's something that you guys should definitely look into.
Yes, that is a good point.
When you were calling my name, I thought you were making the joke about the old slow being still up there. I'm glad it's still up there.
They count. They gave us free food once.
Yeah.
Yeah. No, a lot of Mach 1 rockets, but
Yeah. Are there any questions from the people online? Questions or comments?
I will just say, hi, this is Alakai. I have a few questions, but I'm just going to type them up. I'll send in an email in that chain that you started with a couple of others on the team. This is great, a fantastic presentation. And I just wanted to extend that you've done a lot of hard work. It's exciting to see this progress.
Thank you so much. Thank you. Thank you. Then, if there are no more questions, that concludes our PDR. Some of us will probably be sticking around for a bit if you have any questions, like to ask a certain subsystem or somebody specifically if you would like. But yeah, thank you all for coming.
Yeah, thank you. It was great.
Thank you. Good job.